Hi students, so welcome to this quick lecture on caches. Reusing some slides from a lecture I gave earlier in the year in Singapore. So most of you, I'm really hoping that all of you are aware of what memory is in computers, and that when people talk about memory, they usually talk about like a hard drive or some sort of RAM, what you'd say. But then also there's also more important memory on a computer or in a CPU that most people don't really know of, or let's say look at when they're buying a new CPU, and that's cache. And so today we're going to look a little bit at firstly what is cache in compared to sort of like just what we call system memory like RAM, but also look at how it works and why it's important when we're looking at other topics like worst case execution time, because cache plays a large role in this. So then firstly, memory types. I'm sure that most of you have been exposed to, for instance, like registers when you've been looking at hardware design, on a transistor level, what this is. And so really, registers are like the fastest absolute memory you can get in a system. They're what the CPU uses to store temporary values, sort of like the CPU's temporary variables, if you will. So they are very much in the CPU and thus extremely quick to access. Now, you only have a handful of these on your CPU. I'm talking like 32, 64 of them. Really, you can count them as a human how many of these are on a CPU. Now, these aren't used for storing data. Really, like you don't load an image into the registers or a CPU. They're just there for performing algorithmic operations more than anything inside of the CPU. So we have them, but this is not cache yet. So these are the registers, and these will come. You get taught like when you're learning about how a CPU operates, be it in this course or in another course, you'll definitely deal with the registers. Now, then we have two different sorts of types of memory, what we commonly see on a computer system, right? So we're going to ignore sort of like hard drives and magnetic disk storage and all of this, but look at just RAM. What people say is RAM, and so we have SRAM. And so now this is what we will find in cache, because it's made up of flip-flops. So there's more, like in comparison to DRAM, we're using a lot more hardware, a lot more transistors to build this. Therefore, it's obviously more expensive, right? But given that we're not using capacitors, which I'll mention in a second, it is purely built with transistors, it's extremely quick to access and to get values from. So this is why SRAM is used as cache, but given its price, we can't just slap gigabytes of it into a computer, right? That would be, you could if you're a very, very wealthy chip designer. Now, the more common memory type that we see is DRAM. Now, this is what people would usually refer to as RAM when they're talking about a computer, the average person. So this is sort of system memory. Comes in large quantities because it uses a transistor and a capacitor to build a bit storage, and this is very cheap. But given that we're using a capacitor and it has transient, it's not as responsive as a transistor or like a flip-flop, therefore it's a lot slower. So although we think of system memory like RAM as extremely fast memory, in sort of the scope of computers' memory compared to registers and SRAM, it's extremely slow, right? So this is why we use large quantities of it, of what relatively slow memory for doing, as RAM, so a system storage for sort of like temporary storing of images, of data, of big, large volumes of data. So this is where your programs will get loaded on your laptop and all this sort of stuff. Like SRAM, though, will be much smaller. Maybe you'll see when you're buying a CPU, it'll say something like L2 cache, 4 megabytes, 16 megabytes. Modern, more higher-end CPUs will start coming with like 64 megabytes. Server CPUs will come with a lot more than this, but they're also extremely expensive, right? And this is, I will explain in a minute, why this little piece of cache is so beneficial to the system, right? So, sort of to summarize how all of these different memory types sort of fit together, we can see this figure here on the right. It sort of outlines it very clearly. We have like these processor registers, so they're right next to the CPU, and they're extremely fast. The higher up on this pyramid we are, the faster it is. And so then we have these cache levels, and so I'll explain this in a little bit what this is, but essentially this is just like a hierarchy of cache. Essentially, the closer to the CPU, the faster it is. And so as and different types of cache. Sorry, maybe going into the different types of this is sort of like outside of the scope of this course, is very much like a hardware question. But you can see that the further away, or like sort of the larger the capacity gets, the wider it gets, the greater the speed, right? So this is like the caches will be large, or like a lot larger than the registers, and compared to the registers will be a bit slower, right? And then we'll move down and sort of hit physical memory, and this is what we call as like system memory, or RAM. In general colloquial terms, we just call this RAM. And so this is where we're dealing with like now gigabytes of memory, but we're dealing with speeds that are very fast. Given modern DDR4 RAM and stuff, this is very quick memory compared to what we had 10 years ago, but it is still not on the level of like cache and registers by no means. Right? And then we move down to sort of solid state memory, like SSDs, which I'm sure you're all used to. Again, we're now going to let's say terabytes of storage space, and the bandwidth is like modern SSDs luckily have bandwidth of gigabytes per second, which is still impressive, but it's definitely orders of magnitude slower. And then we get down to mechanical hard drives, which maybe have a bandwidth of a few hundred megabytes per second, but they can have a storage capacity per drive of like, I think I saw some on Amazon the other day for like 18 terabytes or something. So we're dealing with very large storage quantities, but obviously very slow, right? But then why do we have this hierarchy? And so this is what we're going to look at, like why structure your system in this sort of like with all of these tiers. Why not just jump straight from the CPU down to the your hard drive? So why do we do this? So the sort of the requirements of building up this structure means that we have to have a structured memory hierarchy, and in a way that as we move down from the top down this pyramid, the memory will get the higher it up it is, the smaller the memory is. And then we go down, it will contain essentially a subset of the memory below it. So as you can imagine, let's go and have a look at like physical memory. You want to load a program which lives on your hard drive, or let's say on your SSD. You have a program on your SSD, and you want to load this program and execute it. This program will get loaded into RAM. And so the subset of your hard drive, of your SSD, which is the program, will now be contained inside of RAM. Now let's say that you want to load a certain instruction from your program that's now in RAM. This instruction would end up in cache. And so cache has a subset of the tier below it being RAM, right? And so this is how this works. That the higher up you go, it only contains a subset of the memory that's below it. But it gets its memory and what it's containing from the memory below it, right? This means that all of your system's data comes from very much the lowest level, and it'll trickle its way up due to based on when it's being used and cache policies, which we'll get to in a couple of minutes, right? Now, why we do this, why we have these subsets of data kind of going up this hierarchy, is the memory speeds really we can use, but then we can sort of exploit a couple of properties of faster memory, and sort of and also like how programs are executed to get speed increases. Namely this temporal locality, meaning that if you're executing an instruction of a program, there's a good chance that that instruction will get executed again soon. So an example, like imagine you're running a for loop over some array. So it has to execute this for loop 2,000 times. This for loop instruction, just as a pure example, would be loaded. It would go from your hard drive as it's a program, it would get loaded into RAM when the program started. Then when it comes to the program gets to running this for loop, it will load this for loop instruction into cache, and so this instruction now exists in cache. Now as this loop continues to execute, it no longer has to go and get this instruction from the hard drive or from RAM, which is even slower. Well, faster than hard drive, but slower than cache. It has this instruction stored in cache. And so given the temporal locality that is that this for loop is going to be calling the same instructions repetitively, we can make use of this and to get speed increases because we're reading our instructions now from cache instead of from main memory. Similarly, you can imagine that this for loop is executing on an array. Now this is where we can make use of spatial locality, meaning that the items or pieces of locations in memory, ones near them or locations near memory will probably get access soon. So you can imagine you're executing on an array. It'll update one value. So then using spatial locality, the next address in memory will get updated. So these addresses are all sequential in memory, and cache and main memory work on the principle of taking like blocks of sequential memory and moving them up and down the hierarchy. Therefore, if we've moved this, essentially the first array's element into cache, we've probably also moved the second, third, fourth, whatever. So this chunk of array into cache, meaning that we can then exploit spatial locality, that this array's second value is already in cache and therefore it's quicker to access, right? And so this is sort of these two properties that can be exploited for big speed increases, right? So so we'll sort of focus now on on cache. It's smaller, and we cannot obviously it can't contain an entire program. I mean, given modern caches are like a few megabytes, so if the program is really simple, you might be able to contain it, but generally you can't contain all of the required data in your cache at any point in time. So this means we need to have sort of solutions to the problems of, hey, how do I make sure that the data, that the programming instructions that I want are in cache when I need them? How do I go into main memory and get the instructions when I need them? And for instance, like even I've updated my array in cache, I need to put it back into main memory so that I have valid values everywhere. These are the sort of problems that cache presents to us at the same time. So cache then functions, as you imagine, there's like anything in computer science is 10 different ways of doing it. And so when we're looking at cache can have different sort of what we would call a policy, which explains to or sort of tells us how the cache's, let's say, like placement algorithm or algorithm that it uses for accessing cache, how it actually manages the cache it has, right? And so there's like sort of a few common ones that we'll be looking at. And so we're going to be looking at direct map cache, fully associative cache, and set associative cache. Just to name through, we'll really be focusing on direct map cache because it is sort of, if you understand direct map cache, fully associative cache, and set associative cache are a bit, I mean, they are simpler than direct map cache. So then we need to define a few terms then before we sort of look into how these policies work and whatnot. And so the big ones that you'll always hear people talking about, especially when it comes to like worst case execution time analysis and all this, is hits and misses. So a hit is sort of like when you're playing battleships and you want to sort of look at a certain location and you say, oh, hit there, my ship was there. A hit's the same thing in cache, meaning that you've gone to cache to look for a certain instruction, a certain piece of data, and it's there. You found what you wanted, meaning so this is good. This means that it's ready to be accessed in cache. It's usually very quick, and so obviously this brings a large benefit to your program's execution. The more hits you have in your program's execution, the faster it's going to run, right? But then we sort of have the problem that if you have an array in cache and you do get a hit, meaning you do update your value in cache, you have this sort of problem that you need to reflect this updated value that's in cache into main memory. Because if you then want to change your cache's values, meaning sort of get rid of this array that's stored in there, you need to make sure that this data is not just thrown away, and these updated values are not just thrown away, that they're actually stored back into memory so that next time you access these instructions or this data, they're valid and they're not showing corrupt or invalid values. So therefore, when it comes to hits, reading is very simple. If you have a hit, great. What you wanted is in cache. Take it, use it. It's great. We don't have to do anything else. But the problem with sort of like one of the things that we need to deal with is with hits, writing to the cache. So if you want to update an array, and the array is in memory, what happens when the array is there and we want to update the value? So you need to make sure that you're at the same, like there's a few different ways of handling this, that the main memory is updated. And so you can sort of do it in two different ways. You can do what's called write through, meaning that you'll update the value in cache, and you'll sort of write through the cache and also update the value in memory. So as you can imagine, this has a sort of like greater overhead in every single write access. So every time you go to write a single piece of data, you have to do a write to main memory. So this is sort of spreads the overhead out over the entire sort of process. Or you can have what's called write back, is where you update cache And when that block of cache is then thrown out of the cache, let's say you want to load another block of cache on top of where the old one was, where your array was sitting and where you've updated the values, before you then scrap this block, you then write this entire block back to main memory. So it sort of puts the entire overhead at the end of the cache block's lifetime in cache. So both of them have advantages and disadvantages. As you can imagine, write through, if you only have to do small modifications, it won't actually require you to do too many writes, whereas write back can sort of have a lot of overhead, and also if you have, for instance, programs where you're not going to really be updating or like ever taking the data out of cache, then you can use write back to really avoid the need to write back to memory at all, ever. If you can guarantee that this cache's contents is not going to change throughout the lifetime of your program, right? So on the other hand, we have misses. So as hopefully you can imagine, the miss is simply when you go to memory, or you go to cache, better said, and you're looking for some value and you can't find it. It's not there, right? And so this is what we'll call a miss. So this is sort of a problem that we have in reading and in writing, because before, if you had a hit, means that your data was there in cache, easy, you access it. But now we have the problem that if we're looking for data and it's not in the it's not in cache, we have to then go and find it. So how do we do this? So generally, like in reading, you'll store the CPU, because the CPU needs the value, so it can't really do anything until it has this value. It will then fetch the block from memory, and so we'll deal with like what I'm talking about with blocks and how this is exactly done in a little bit later. But essentially, the data that you need is taken from the next level down in the hierarchy. So this is most likely system memory, and it's loaded into cache, right? And so now we're at the point where we have essentially a hit, right? We have the cache loaded and the value we want is in cache, and so we can just continue on with the program's execution using the values that are now in cache. So then writing here is sort of the same thing as when you have a hit, but you firstly load the cache line, right? Or you don't load it. So you can either write directly into memory and sort of negate the need to load the block into cache first. So if you could be sure that you're not actually going to need to access this block anymore, then why bother loading it into cache? Because when you do a write, you have to write to main memory anyway, right? If you are going to use the cache block again, then it would make sense to firstly load it into cache and then to write into cache, right? Using either write through or write back writing policies. That's also something to take into account. So, hits versus misses. Now, as you can imagine, misses, the loading of main memory into cache is extremely slow as far as in computer terms. So reducing the amount of misses means we reduce the amount of times we have to load system memory into cache. So this is an extreme speed increase when it comes to execution of computer code. And so therefore we can do a few different things, or the sort of things that we want to sort of strive for when it comes to writing programs, or more so for compilers and these parts of the software. They want to optimize to decrease the amount of misses that we get. And so we can do this in sort of the most common way of doing this on a software level is using associativity. And so this is, as we were mentioning, sort of before, wherever it was. So this is sort of to do with like temporal locality and spatial locality, in that things that we're using, or like the data's close together, structured in a way that the accessing of cache is optimized. Then also one thing we can sort of do on a more hardware level is that we can increase the sort of the hierarchy that we're using, this memory hierarchy, to include multiple levels of cache. And so this is when we see this L1, L2, L3 cache. They're generally like different types of cache, different speeds. And so by tiering it even more, we can add even more levels of this sort of, is it in the lower level of memory? No, it's not, loaded into memory kind of behavior. But because we have in more levels, essentially with cache, which is extremely fast memory, we can then decrease the penalties of a miss. But obviously, then you have a more complex system, and also you can have misses on multiple levels. So you can essentially increase the penalty, but in general, it also will decrease the penalty that you have. So now, the next sort of term that I want to define is a cache line, because I've been talking about blocks of memory, loading blocks from main memory up into cache, and you sort of dealing with these blocks of memory. And so to define what a block is, we sort of have to talk about what a cache line is. Now, a cache is structured into lots of different chunks, meaning like a 4 megabyte cache is actually structured into, let's keep it really simple, 4 blocks of 1 megabyte. But it's generally a lot more. A lot smaller than this. Cache lines are generally like 64 bytes or something. I just can't do that sort of maths in my head. So the cache is constructed of all of these little blocks of memory, and we will refer to these blocks as a cache line. So if my 4 megabyte cache has 4 1 megabyte cache blocks, it has 4 cache lines in it, right? And so this just means, we're splitting up our cache into these cache lines, which represent memory blocks, and the cache is a collection of these, right? And so when we're dealing with loading memory into cache, we'd only ever deal with complete blocks. And as you can imagine, the buses in computers, CPUs and whatnot, they deal with generally parallel data transfer. So if you want to move 8 bits, let's go to an 8-bit microcontroller, and you want to move an entire byte into some memory, there'll probably be 8 wires connecting each bit. So you can move the entire byte in parallel at the same time. This is sort of the same principle with caches. You don't just load a byte from memory, you load a block of memory, right? And so if you have, let's say like we have on this slide, a 64-byte cache block, like a cache line, meaning every time you go to read a memory address from main memory and load it into cache, you will take the entire block where this memory address falls. So it falls in the middle of a in the middle of a memory block, you'll take the entire block. If it falls at the beginning of the memory block, you'll still take the entire block, right? So every memory address falls into some block on the system of this specified size. And so this size is system architecture dependent, generally around the 64 bytes or so, right? So then we can sort of start looking at these policies. We know that we have these blocks, and we only ever deal with these absolute blocks of memory. And so if we can now think about, okay, cool, this means that every single memory address in our system, in main memory, in RAM, and in cache, of course, has, it is part of a certain block. So there'll be 64 memory addresses on, or if it's a 64-byte byte block, and we're on a 64-bit system, meaning that we have, we have that 64. Sorry, ignore the 64-byte bit system. We have 64 bytes of storage, meaning that those 64 bytes all fall into the same block, memory block. And so this means that they'll all get moved into cache together into a certain line, because the blocks and the lines are the same size, and they will always move a block into cache at the same time, meaning we'll completely populate a cache line every time we want to load something from memory, right? So then direct map cache tells us essentially, or the way it works, is that based on the memory address of a cache, of a value in memory, it will only ever get loaded into a certain line. So if we look at this super simple example of my 4 megabyte cache with 4 1 megabyte lines, every value in every location or every memory address in the system's memory will only ever get put onto only one of those lines. So every time it gets put into cache, it'll always go back onto the same line. And so this is why it's called directly mapped. And so I'll run through a quick example of how this exactly works, how it determines where it wants to go, but it's really quite simple. So a quick visual example, we can see on the left here, I have my main memory, with my memory addresses. I just have here 16 memory addresses, and I have here my very simple cache. Now we don't have to deal with how big it is, we don't really care. All we want to know is I have 4 cache lines. So I have 16 bytes in memory, and I have 4 cache lines. And if we can see here, this means that every time I want to load the memory address that falls inside of this first memory block, it'll get put into the first cache line, the 0th cache line. Similarly, the 2nd, 3rd, and 4th, they'll map to the 2nd, 3rd, and 4th cache lines. And then it just sort of repeats. And so the 4th one, the 8th one, and then the 12th one, they all also get mapped into 0. So this means that if we're running our program and we want to look and we want to use this one here, this memory address on the 8th one, we will know that it's going to be mapped into here. So we know which cache line we have to check. And so this is a sort of, the key of it is that we know essentially via sort of like a lookup table functionality where any given memory block in our system will be in cache, meaning we know the cache line it falls onto. And so this is very simple how we figure this out. So every memory location on the system has a memory address. Generally it'll be like on a 64-bit system, it'll be a 64-bit address. And it's split up into 3, like using direct map cache. The other policies have slightly different ways of doing this, but in direct map cache there are 3 regions or 3 fields inside of each address. So you can imagine that this entire thing here on a 64-bit system is 64 bits. So essentially there are then 3 little sort of subsections or subsets of the address that tell us certain things. If we look firstly at the offset, so imagine here, my basic example of a 4 megabyte cache with 4 cache lines. This means that every cache line is 1 megabyte in size, and so it can store 1 megabyte worth of addresses, like of individual addresses in it. So we need a way of saying, okay, I know that my block is in memory, so my value I want, its megabyte block is loaded into cache. I need to specify exactly which byte I want. And so that's what the offset does. It tells you if my block is in memory, how far down from the top of the cache line do I have to iterate to get the exact byte I'm interested in. And so that's what the offset does. It specifies where in the cache line the data, word, or byte is located. But this is actually not the first thing that you'll use when you're accessing cache or using cache. It's actually the last thing that you'll use. What we are, the one thing that we're really interested now is the index. And so we're saying here, for instance, an example, the 0th, the 4th, the 8th, and the 12th cache lines all map into this 0th cache line here. Now, there's a super simple way of sort of knowing which ones map into which. And if you've sort of caught onto it here, we have 4 cache lines, and these guys here, they all are modulo 4, not modulo 4. And if we look at the addresses of them, if we looked at them in binary, they would also all show us a certain thing in the index. They would all have a 0 in the index. So as you can imagine, the memory addresses for these here will have 2 bits that can either have the values 00, 01, 10, 11. And so those are the values 0, 1, 2, and 3. And so those 2 bits in the index, essentially we can look at them and go, okay, cool. For instance, here it would be 0, 0, and so we know directly just from looking at those bits that we have to look at the 0th cache line to see if our data is there. So the first thing we'll do when we're trying to find something in cache is we'll use these index to find out the cache line that something falls on. But then how do we know that what's in the cache line is the data that we're interested in? This is the sort of the tricky part of it, right? Like we have so many blocks on the system. We can find out from the memory addresses which index they are mapped to, but how do we know that the block we want, the block that we have in the cache is the block that we want? Now, if you go and write out all of these addresses here in binary, they'll all have the 00 in the index field. And that will tell us that they all map to these to the 0th cache line. Now, this offset here, it will be like where inside of this cache line it will be. So in this example, it's not really applicable. But what the tag will then be is the remaining sort of part of the address at the top that will then let us compare it to the metadata currently stored in the cache here. And the metadata stores the tag of the currently loaded block. And we can compare the tag to the metadata's tag to see if it's the same cache, so the memory block. We'll see in an example in a minute that this tag is also unique for all blocks that fall onto the same cache line. So the tag is obviously not unique in the entire memory, but given any cache line, there is only ever one memory block with each tag. And so that's what the tag is. It's used for us to check against the metadata, which is the tag of the currently loaded block, to check if the block in memory is the block that we are after. So let's have a little look at an example, hopefully make it a bit clearer. So we have a 32-bit system, meaning we have a 32-bit long address. And in this case, we know we have a cache line that is 64 bytes. And so meaning that there are 0 to 63 different offsets that any particular memory address can have. How many bits do we need to represent 63? We need 6. And so we know that our offset here is going to be 6 bits. Because in this case, we can show the values between the first byte and the last byte by using these 6 bits. And so that's why we know we have a 6 bits offset, because we know we have 64 bytes in each block. Then we get to the tag, and so sorry, not the tag, the index. And so the index is how many cache lines our system has. So this was an exam question, and I said, hey, we have a system with 32 cache lines and 64 byte memory blocks. You will know just from that sentence that I have a 6-bit offset and I have a 5-bit index, because the index will just represent which of the 32 cache lines it falls onto, right? So for this memory address, we can look at these bytes here, so these 5 bits, and say, okay, we have 1, 2, 4, so this is 7. So it's going to fall onto the 7th cache line, obviously 0 indexed, right? Then the remaining bits, so like these ones can be read out from, okay, we have 32 cache lines, so that means it's 5 bits, we have 64 bytes, this one is then 6 bits. The tag is essentially everything else. And so if we look back at here, we can see it's just m minus n minus k. You generally figure in, like let's say in an exam question, you'd sort of go and figure out these two, and then you just essentially say the rest of the address is the tag. So if we were to say, like, this tag here is quite long, and you'd be like, okay, the next memory address that comes after it, so you can imagine it's all the same, but on the end has a 1. Sorry, let's just say the next block in memory that comes after it, meaning that here, on this one here, it has a 0, 0, 0, 1. It falls onto a different cache line, even though it has the same tag. Therefore, we're not going to get this tag again on the 7th cache line. So this tag is unique to this memory block, given that it falls on the 7th cache line. And so this is how we can use the tag to check the block is the correct one that we want. Right? And so when we save a block in memory, we load its tag. So we load this, whatever this is here, into what was called the metadata. And so each cache line has a metadata where it stores the current block's tag, right? And then this is used for comparing against new sort of requests to see if it's correct or not, if we have a hit or if we have a miss. So therefore we have these 3 sort of chunks, and then the process of using direct map cache lookup sort of comes down to, okay, firstly we can look at the index of the address. It's just sort of like a lookup table style thing. Say, okay, cool, like in our example we had 7, so we'll just go and directly look at the 7th cache line. Then we can say, okay, is this block in cache the one that we are after? We know the memory address of the block we want, therefore we have the tag. We can just compare the tag to the tag stored in the cache line's metadata and say, okay, are these the same? If it's the same, we have a hit, we're good. we can then use the offset to go step into the memory block in the cache and access the byte or the data that we're after. But if it's not, we know it's a different block in cache and it's a miss, so we have to then go and load the cache line from memory and update it because we don't have the data we want. Right? And so that's how the direct map cache works. It uses these three little sort of subsections of the memory address to look up data in cache directly, meaning it knows exactly which cache line it's going to fall into. So this is going to be the main policy that we'll look at in this course, because I think it's sort of the most, it sort of makes complete, as we'll see now when I talk about these other two, it's sort of, if you understand direct map cache, you should understand these other ones, right? And so let's quickly then look at the other two policies, common policies, and this is fully associative cache and set associative cache. Looking just directly at fully associative cache, what it means really is that a memory block can be placed anywhere in memory. So given some memory block, we can put into any single cache line. And so this means that we don't have an index. So the address is made up of an offset, meaning, because we still need to know which byte exactly or where the data location is inside the memory block, and it will have a tag because we no longer have a memory block mapped directly to a cache line, right? So this means that placing a block is slightly different because we don't have this, okay, cool, put it in this cache line sort of thing. So what's going to happen is that when we want to place a block, essentially, we just search cache for a block that is free. And so, like when we restart our computer, if we're using fully associative cache, every block is initially marked as free, and then they'll slowly get filled. And then when we get to the point where every cache line is full, therefore none of them are free, we then have a replacement policy. And so the replacement policy determines where we should put it. So maybe it'll overwrite the oldest block first, or the one that's least used or something. And so there's a whole different replacement policies. We're not going to go into this. But essentially, when we want to then look for a block that we've placed in cache, we have the problem that we don't know which cache line, so we just have to slowly step through cache, and so it's very slow in the lookup, and we're looking through each cache line and comparing the tag to see if it's the same, if it's the correct block. So it is very slow in this regard, right? Then we have a hybrid solution, set associative cache. So it's a mix of direct map cache and fully associative cache. It's a mix in that we have we take collections of cache blocks and make them into a set. Sorry, not cache blocks, cache lines, and make them into a set, right? And so we also have an index field, but the index field tells you where inside of each of these sets, right? So let's say we have sets of 4 cache lines. That means that we're going to take our cache and break it up into lots of little chunks of 4 lines. And then we'll have a 2-bit tag that will tell us where inside of these set it falls. But into which set a cache line gets put is completely random. And not random, but it's done the same way as in fully associative cache, in that there's no index to sort of reference. It'll look for the first one that's free and place it in there, right? So hopefully that makes sense how that works. So that's really the end of this lecture. It's not the biggest topic, but we're going to need it when we're talking about worst case execution time. It's also a good one for asking small exam questions. And when we're dealing now with worst case execution time, it's going to be really important that people understand what a hit and a miss is. And so hopefully by understanding slightly how the cache works, how we have these direct map cache where we know if a cache line is populated with data or not, know what hit and misses. You'll sort of understand when this happens, why it happens, and then now also understand through the memory hierarchy that misses can be extremely detrimental to the execution time of your program. So thank you for your attention.